Welcome to the third video in our series on encryption. We're going to cover practical ways of implementing the types of encryption we covered in the last two videos. As we've mentioned repeatedly, the biggest issue with encryption is keeping those keys secret. With secret key encryption, you're giving the key to someone else, and you have to trust them. If Alice gives the secret key to Bob, she has to trust him not to turn around and give the key to Eve. We talked about private key encryption and how Alice doesn't need to trust Bob, since the public key she gives Bob can only encrypt messages and verify digital signatures. Only the private key can decrypt and sign messages. Bob can make sure that only Alice can read his messages and can verify a message was sent by Alice, assuming that Eve hasn't stolen the private key. But there's a weakness here, and that happens when Alice first gives Bob her public key. If Eve intercepts this message, she can substitute her own public key for Alice's. If she then intercepts Bob's messages to Alice, then Eve can use her own private key without having to steal Alice's and decrypt the messages and sign her responses. Bob thinks he's using Alice's public key, but he's really using Eve's. So we need a method of doing a secure key exchange so that we can verify that we have the correct key. If Alice and Bob get on the phone or a video chat, then they can make sure Bob can send test messages to Alice encrypted with her private key. They'd be able to tell instantly if Alice can receive and decrypt the messages, and if she can't, if Eve is pulling something, then they'd be able to tell right away. And since Bob just sent a harmless test message, Eve doesn't get anything important. We also need a method of key revocation. If Alice learns that her private key has been compromised, if she thinks there's even a chance that Eve has stolen it, she needs to let Bob know and generate a new public-private key pair and send the new public key to Bob. PGP is a de facto standard for securely encrypting email. People can exchange public keys through key servers like this one at MIT. But since anyone can upload any key they want, how do you know that you're really getting the right key for that person? If Bob and Alice exchanged keys in person or over the phone or video chat, they know they got the correct key. They can then trust that key. Bob can sign Alice's key using his private key and give it a level of trust. There are 5 levels of trust in the PGP standard. 1. I don't know. 2. I do not trust. 3. I trust marginally. 4. I trust fully. And 5. I trust ultimately. Bob and Alice each trust their own keys ultimately, because it's their key after all. But they shouldn't do that with any other key. Bob should not trust Alice's key ultimately, and vice versa. What they should do is an indirect trust, which happens when they sign the key. So Bob signs Alice's key, and he can give it one of 4 trust values. 0. I don't know. 1. I have done no checking. 2. I have done casual checking. And 3. I have done very careful checking. Since they actually got together, exchanged keys, and verified them, Bob can sign Alice's key at level 3. Let's bring in a third person, Carol. Carol has also exchanged keys with Bob. Although she hasn't directly exchanged keys with Alice, Bob has, and Carol trusts Bob enough to trust his evaluation of Alice's key. So she doesn't need to go over the whole thing again with Alice. As long as she trusts Bob enough to make sure Alice can be trusted, she can trust Alice too. This is called a web of trust. A key can be trusted by answering 2 questions. 1. How many other keys trust this one? And 2. How trustworthy are those keys? If Carol is sloppy about which keys she trusts, Alice and Bob might not trust keys signed by her that much. Also, Alice's trust of Bob means that since she trusts Bob, she'll accept Bob's evaluation when he trusts Carol's key at a lower level or distrusts Eve's key entirely. Bob can also generate a new key anytime he wants and sign it with his old key to let people know it's genuine. He can then revoke this older key. Keys can also be set to expire at a certain date. Threema is a smartphone app that lets users send secure messages from one smartphone to another. Unlike PGP, there's no web of trust here. They do have public keys on their server, but that only gives the user an orange verification level. The way to get the green level is to exchange keys directly, and here's how it works. Alice and Bob get together with their smartphones. They pull up the Threema app and have it display their public keys on the screen in the form of a QR code. They then scan the QR codes directly from each other's phone. Since they can be sure that no one else has monkeyed around with this exchange, they trust each other's key to the highest green verification level. This method doesn't work very well, though, for things like public web servers. When you shop at, say, Amazon.com, you need to be able to trust the encrypted connection with Amazon without having to run around and find someone you trust to sign their key. For this purpose, we use a trusted third party called a certificate authority. Bob gets a certificate from a trusted CA and puts it on his server. The CA has digitally signed his public key and verified that it belongs to his website. The private key, as usual, is held solely by Bob on his server. When Alice connects to Bob's server, she gets the certificate and checks its digital signature to make sure it was signed by the CA. At that point, she knows she can trust that site has the correct public key for Bob's server. The third method of implementation is TNO, or Trust No One. This is used when Alice needs to secure her data and doesn't need to exchange it with anyone else. Financial records, for example. Alice may want to use a third-party service like Carbonite to back up her data online. By default, Carbonite manages the encryption keys, which means that they can access the unencrypted data. If Alice wants to make sure no one else can read it, or needs to comply with something like HIPAA for medical records, Carbonite gives her the option of making her own encryption key. She then keeps track of the key herself, and no one else can decrypt the data. But there are disadvantages. First of all, Alice will lose access to certain features, such as accessing her backup files from her smartphone. Second, Alice has to make sure she doesn't lose this key. If she does, she will lose access to all her backup files. Alice has other options for encrypting files on her hard drive, laptop, or cloud storage. The 7-zip archive program has an option to encrypt the archive with strong, industry-standard AES 256 encryption. She picks a secure password and enters this into the 7-zip interface. This password is then securely turned into an encryption key which encrypts the files in the archive. No one can get the files out of the archive unless they know the password. So whether it's on her hard drive, backed up with Carbonite, or put on a cloud storage provider like Dropbox, no one can access the contents without getting her password. Trust No One means that Alice can do whatever it takes to keep the key secure, but if she ever loses it, she's out of luck. So in this video, we've covered ways of implementing the encryption methods we talked about in earlier videos. We talked about a key exchange between individuals who trust each other. We talked about verifying a key with a trusted authority. And we talked about Trust No One security, where only one person has and needs the encryption key. In the next video, we'll complete part 1 by looking at issues that arise with those all-important random numbers.